Permutations are also extended. There's things called distinguishable permutations. And what we're going to do is we're going to look at distinguishable permutations. And so I'll go right to the example. Right? Someone's developing houses. And they're going to build 6 one-story houses, 4 two-story houses, and 2 split levels. And so there's a total of 12 houses they're going to build. And so the idea is, one-story, two-story, two-story, split level, two-story, and then the rest one-stories. Right? That's a permutation. The street could look like this. Or it could look any permutation of this. So we want to figure out how many kind of different developments you can get by just stacking in these different types of houses. But because of material costs and buyer demand or market research, this is the ratio of the 12 that you want things. You want 6 of them to be this. You want 4 of them to be this. You want 2 of them to be this. So how many patterns are there if we're forced to pick 6 of these, 4 of these, and 2 of these? And so what you do, and this is called distinguishable permutations, is we're going to give these variables. So this is n. That's the total number of houses we need. And then this is n1, n2, and n3. The number of particular things. And so to count all of this, we take n factorial, 12 patterns we can have, but those 12 patterns are going to be divided by possible permutations of n1, n2, and n3. And of course you could have more than 3 things in here, and so this would go up to however many things that you have. But always, the things that you have add up to your total n. And so this is called distinguishable permutations. All right, so on this house example, our distinguishable permutations, we have 12 factorial divided by 6 factorial, 4 factorial, 2 factorial. And well, I'm going to use my trick here. I'm going to take the 6, and that's going to leave me with 12, 11, 10, 9, 8, and 7. And then I'm going to expand these out on 4, 3, 2, 1, and then in 2 times 1. And I'll notice that the 4 and the 3 give me the 12. And then I have 4 left over. So I'll divide that by 4 and I'll get 2. This just makes it easier on my calculator. But there's 13,860 distinguishable permutations amongst this type of housing. Key on this is all the little n's, all the little objects that you're counting, all of these things add up to big N. 6 plus 4 plus 2 is 12. That's a key takeaway with distinguishable permutations. Well, maybe order doesn't matter. Maybe I can pull things out and it doesn't matter what order they come in. So for example, let's say that there are 16 bids on a contract, and I'm going to pull out 4 bids. I can only take 4 bids. Right? Well, Acme Building doesn't care that it came before Zen Building. Right? If this order was flipped around, it wouldn't make a difference. We got the bid. We got the job. And so these are called combinations. And we write combinations with the total number of things, combinations, how many we're grabbing. And it's a slight modification on the permutation. If I were to just have this would be the same as the permutations where I chose. And I could be saying, here I've chose 4 things. But we need to get rid of the repeats. We need to divide the repeats out. We need to divide how often the things I chose repeat. And so that's how we do it. We divide the repeats out by putting r factorial down there. Let me get my size back. There we go. And so it is the permutations dividing out the repeats. And that's what that r factorial is. And of course r has to be less than or equal to n. But it can be equal to. So let's look at this. If I have 16 bids, I have 16 bids and I'm only choosing 4 of them. So 16 choose 4 equals 16 factorial over 16 minus 4 factorial times 4 factorial. Now 16, I'm sorry I keep hitting that one key off on the side of my tablet here. It jumps over. We'll try to disable that. So 16 minus 4 is 12. So that gives me upstairs 16 times 15 times 14 times 13 because the 12 and everything else. And then 4 factorial is 4 times 3 times 2 times 1. So that 4 will turn that to a 4. That 3 will turn that to a 5. That 2 will turn that to a 7. So this is 4 times 5 times 7 times 13. Or, let's see here, 4 times 20, 140, 140 times 13, or 1,820 combinations. And so combinations are how many we can get when we choose without order. Now the book has a nice little chart, and it says, well, if you have one event occurring m ways and another occurring n ways, that's your fundamental counting principle. And so the total possible ways you have of one event m ways and another event n ways, you get m times n. Now, if you have n distinct objects, and you want how many ways you can arrange them, or what's called permutations, then that's n factorial. If you have n distinct objects, and you take r at a time, then that's n permutations r, or n pick r, as I kind of mentally tell myself. That's n factorial over n minus r factorial. I have n objects, and I have n1, n2, n3, and so on, distinguishable objects in them, or sub-patterns, so to speak, then that's n factorial over n1 factorial, n2 factorial, n3 factorial, all the way up to times nk factorial, as long as n1 plus n2 plus n3 and n sub k all equal n. That your little distinguishable things all add up to your total. But if order doesn't matter, and I have n objects, and I pick r of them with no order, that's n combinations r, that's n factorial over n minus r factorial. Right now that's the same as the permutations, but then I'm going to divide out all the ways the ones I picked could repeat. I get rid of the repetitions. I divide out the repetitions. And that's called combinations. And these become very, very, very useful in determining probabilities. And give an example of this. So let's say there's an advisory board. I can change colors here. This yellow's glaring on my eyes. There's an advisory board of 17 members. 3 members will serve as the chair, secretary, and the webmaster. Those are positions that have to be held. If we randomly select the 3 board members, if each member is likely to serve, and we randomly select one, what's the probability of being a board member? So there's 3 distinct things. Order is important. There's only one favorable outcome. And so, right, if I grab these 17 people and I get them into the right positions. So, the number of ways I can fill these positions are 17, pick 3, which is 17 factorial over 17 minus 3 factorial, which is 17 factorial over 14 factorial, or 17 times 16 times 15. So there's 4,080 ways to choose these people, to choose these 3 positions. So there's 4,000 ways these 3 positions could be filled. But right now, these positions are filled one particular way. Order is important. And so if I randomly grab the three people, there's only one way these 3 things are filled out of the 4,008. So the probability of picking 3 board members in position is equal to, there's one way of doing that, out of 4,080. Okay. Or about 0.02%. That's the probability of it. But notice how we took a probability out of it. So, right, you think of what this is saying. It's saying there's 17 people and they're on a board. And I just point to 3 people randomly. And I say, you're the chair, you're the secretary, and you're the webmaster. This is my chance of being right, knowing that these positions already exist inside the ability to figure out who's who. And so notice one of the things here is we didn't have a large number of things. We only had 17 people that could fill 3 spots. But that already generates a large quantity of unique ways those 3 spots could be filled, and that generation creates some small probabilities. And that's going to be the nature of the probabilities that we see. Let me come back up here. Do another one. Okay, in a standard deck of cards, there's 52 cards. Alright, and it's divided into 4 suits of 13 each, right? So there's 4 hearts, 4 diamonds, not 4, sorry, there's 13 hearts, 13 diamonds. There's 4 suits. 13 of them are hearts, 13 of them are diamonds, 13 are clubs. I feel like I'm drawing a package of Lucky Charms here. And spades. And so if I want to, there's a particular combination called flush where you get everything of the same suit. And so we want to know the probability of being dealt 5 cards that are all diamonds. Now, it doesn't matter which one I get first or not, so order doesn't matter. Right? It doesn't matter if my first card's the ace or if it's the 4. I just want all diamonds. And there's 13 ways of choosing diamonds. So this is 13 combinations of 5, or 13 factorial over 13 minus 5 factorial. That gives me all the permutations, but I need to not care about the different order they come in. And that gives me how many ways I can get this. What I want. My positive outcomes. But that's not how many ways there are to deal 5 cards. To deal 5 cards, there's 52 cards I can deal from. And so my probability is the number of favorable outcomes, 13 choose 5, divided by the sample space, which is this, 52 combinations 5. And so my probability of 5 diamonds is I have this many ways that are good outcomes, good events, and I have this much in my sample space. And if we plug this in to our calculators or into Excel, we get 1,287 for the numerator, and we get 2,598,960. Right? So if you're thinking of a poker game where you're dealing 5 cards, that's how many combinations of individual hands there are. 2,598,960. And so your chance of being dealt all diamonds right off the bat is 0.05%. But notice we turned the thing we want is the number of outcomes in our event and how many different ways there are to get things as the number of outcomes in our sample space or our probability space, whichever way. I think the book keeps doing sample space, I keep saying probability space. I hope I don't confuse everyone. I'll try to catch myself. And so notice, again, we're able to count a large number of things rather quickly with these tools. And so combinations and permutations become ways for us to count large number of things. All right, that ends chapter 3, and I'll start chapter 4 in a second here.